When we work with parametric coordinates, we're still working in X and Y, but that itself is not a requirement. There's another entirely separate coordinate system based on the idea of polar coordinates. How many of you have seen polar coordinates before? Okay. We're going to change the grid we're working on. We're no longer going to work in the X and Y grid. Instead, I've got a brand new piece of graph paper. You can still see the x-axis clearly on here. I've got this line running all the way across. I've got a y-axis, but I've superimposed that with a set of circles and a set of angular measurements instead of a Cartesian xy grid. This is our polar grid. We have a pole, the origin, and for convenience, I will put the primary part of the x-axis as my polar axis. So normally, when I think of polar coordinates, what I think of looks like this. But I almost always see it over this particular piece of graph paper. And for the record, this piece of graph paper is older than I am, my father. This is a photocopy. But this is more common in orienteering and navigation, in places where you don't have a convenient grid laid on you. If you go sailing, you use this. If you took pre-calc, we did that, but we oriented our polar axis with north. And that worked, and we took bearings from this. But now I want to put it on the Cartesian plane, and then if I pick a point that's not the origin, I'm going to measure the coordinates of this point differently. Instead of measuring x and y, I'm going to measure the distance directly to that point and call that a radius. And I'm going to measure the positively oriented angle from the polar axis to the ray connecting the pole and the point, and the coordinates will be r and theta. First thing I notice is that now a point is not uniquely defined by its coordinates. Here's a point. Again, my standard behavior is to overlay the pole with the origin and overlay the polar axis with the positive half of the x-axis, assuming that's what I've done here. Where is this point? Physically, where would you point to it on the plane? It would be in the first quadrant. It's going to be 3 units away from the origin at an angle of pi over 3. So pi over 3 is 60 degrees. And I go out 1, 2, 3 units. But I can give you another set of coordinates that land in the same spot. What's another angle that's coterminal with that ray? both of those sets of coordinates describe exactly the same point. As a matter of fact, let's extend the ray down into the third quadrant. What angle takes me here? Yeah. Close, but no. 4 pi over 3 goes this way, because that's a positive angle. And the angle I drew is negative. But it's coterminal with 4 pi over 3. What angle would this be?
2 pi over 3.
Aha. But if I'm facing this direction and I want to end up here, I have to walk backwards, don't I? So I could just as easily say that the point -3, 4 pi over 3, or the point -3, -2 pi over 3. All 4 of these describe this one point, P. And what that means is that polar coordinates are not unique as opposed to Cartesian coordinates. Every point on the plane has one and only one set of x, y coordinates. But they have multiple polar coordinates. I can add any multiple of 2 pi and hit the exact same point. And that's what we did here. We subtracted 2 pi. K is -1. And that'll put me at the exact same point, just going the other way. Also, if I make the r negative, then I have to add 1 pi, or any odd multiple of pi. All of these mean that I can end up hitting the same point more than once, but that actually doesn't strike me as a bad thing. We did that with our parametric graphs too, didn't we? Remember the circle? We were around circle once, then we were around circle 3 times. It was the same physical set of points. We just covered it more than once. I like to think of this as Boy Scout navigation. I don't know how many of you were Scouts. Boy Scouts, Girl Scouts, Cub Scouts, Brownies, whatever. One of the things I did in the Boy Scouts was orienteering. They gave me a compass and left me in the middle of nowhere and said, find your way back home. They gave me a map too, so I knew where home was. But I would find the direction, figure out how far I had to go. Well, that's a theta and an r. This is orienteering. Questions? I overlaid my polar coordinates on the Cartesian plane. If this is the x-axis, and this is the y-axis, and this is the origin, I should be able to find an xy set of coordinates for P as well, shouldn't I? And this is why we often call Cartesian coordinates rectangular coordinates. It's because the base shape on the graph paper is a square, a little rectangle. And in polar coordinates, the base is a circle. And our little shape is kind of a wedge. All right. Let me deal with the point we were looking at 3 pi over 3. Cast your mind all the way back to trig. Appendix D, the first week of Calc 1, or your trig class if you took it here. On this picture, add a right triangle by drawing a perpendicular from P down to the x-axis. And now, if I want to think of our point in x and y, then x and y are the sides of that right triangle. How do we find x? For the Pythagorean theorem, I need to know 2 of the 3 pieces of my triangle. And I have x and y and 3, I only have 1. I absolutely could. Which trig function involves x and the other known side 3? Aha! Cosine of pi over 3 is x over 3. And then Dom defined y. Started to write x again. That was a bad thing. Which means I have x is 3 cosine pi over 3, and y is 3 sine pi over 3. And out comes the unit circle in my brain, and I remember what those numbers are: cosine of pi over 3 and sine of pi over 3. And if you don't remember it, we use the hand trick. Remember the hand trick? Sine counts up, cosine counts down. If you're doing sine, start your pinky at 0 and count up. But look at the angles: 30 degrees, 45 degrees, 60 degrees. Hold my hand and make a 90-degree angle. Those are the 3 in the unit circle, aren't they? So 0, 1, 2, 3. Sine is square root of 3 over 2. Cosine starts with your thumb and counts down. 0, 1, 2, 3. So 0, 1 to get to pi over 3, square root of 1 is 1. Cosine of pi over 3 is 1/2. Ta-da! Now, this again gives me an insight into why polar coordinates repeat every 2 pi, because cosine and sine repeat every 2 pi. So I'm going to get that repetition built in to my Cartesian coordinates. How do I generalize? If I have any point go about it exactly the same way. With the cosine and sine, because I'll draw that little triangle in. Like that. That allows me to convert any point. You can define every point on the plane with a positive radius, except 0, the origin. But every other point on the plane can be defined with a positive radius. You don't have to use negative radii. You can. Where is the point 2 pi? Leo.
2 pi will be over there, so it's on the pi right at -1 sine, that would be 0.
Aha. Because I'm on the left side, all the way over here, I'm at -2, 0. Questions? It takes a while to start thinking in polar coordinates. This is not an intuitive shift. I love working in polar coordinates. I've been doing this for way too long. And this is more convenient to the work I do in complex variables, but it's a very interesting change of perspective. What if I want to go the other way? I had r and theta, I wanted x and y. What if I tell you that my point is -4, 4? My very first reaction, please draw the picture. Tell me where this point is in the plane, and then we'll figure out how to get the coordinates. Yeah?
I think that the point would be like in the second quadrant.
Okay. Now, I need to find my r and my theta now. Now I have two sides of the triangle, don't I? I have x and I have y. So now I can do exactly what you wanted, Maddie, and I can say, oh, r squared is x squared plus y squared. I can use Pythagoras to get r. And in this case, I get r squared is 32, which means I have a choice to make. I can decide to use a positive r or a negative r. It is up to us. By the way, I could simplify this square root because 32 is 2 times 16. Square root of 16 is 4. You don't have to. You can leave it square root of 32. I'm not going to object at all. Somebody make a decision for me. Should r be positive or negative? Leo.
I think it needs to be negative, this is the second quadrant, x is negative.
Okay. If I'm going to use the negative one, then I'm going to say, oh, I want to back up this far. And that means I need to be facing not into the second quadrant, but into the fourth quadrant. What angle in the fourth quadrant do I get? Oh. I can do it either way. I can use 7 pi over 4 and go around this way, or I can use minus pi over 4. How did you come up with minus pi over 4? Because it's what? It does look like it's cut in half. That could be my crappy drawing. I'd like a more analytic way. So how could I do it analytically? Yeah, it has a slope of 1, right? Well, negative 1. All right, wait a minute. What trig function gives me a negative 1 with 45 degrees? Negative 45 degrees. Tangent. So I can think of it in terms of tangent then. And if that's the case, well, then that's y and x, isn't it? 4 over negative 4. Y over x is tangent. Tangent of theta is y over x. And now I have conversion equations that go the other way. Now here's the problem. When I use the inverse tangent button on my calculator, inverse tangent always gives me an angle either in quadrant 1 or quadrant 4. It never gives me an angle in quadrant 2 or quadrant 3. So I have to adjust. If I want the angle in quadrant 2, I need to know that when I do the inverse tangent, I'm going to get the angle in quadrant 4. And to get it over there, I need to add pi. So if I wanted to use the positive r, then I could say, oh, theta is minus pi over 4, but then I've got to go back that way and add on a multiple of pi. And that's why I say you can use positives or negatives for r, whichever one you like better, to go with whichever angle you like better. But it's your call. Leo, you were trying to show me something on your calculator. What were you showing me?
I was sorry, I'm inverse tangent theta 4 that's minus 45 degrees.
Right, and I'm going to work in radians almost always. I'm going to rarely use degrees here because I find that working in radians is more convenient in this setup. But absolutely, it gives me negative pi over 4. It gives me negative 45 degrees. But now I have my conversion equations. I have the ability to get from r and theta to x and y, and the ability to get from x and y back to r and theta. This will be important later. Questions? Grab your calculators. Because if I want to draw things in polar coordinates, I absolutely 100% do not want to spend my time with this piece of graph paper drawing this crap by hand. And I'm almost 100% sure you don't either. Which means I need to get out of parametric mode. And look, right there, right next to parametric mode is polar. Please make sure you are in radians, the line above that. If you are not in radians, please change yourself to radians. Never leave radians again. If you need degrees, you can hit second apps, because right above apps, it says angle, and there's a degree mark. Oh, helps if I hit the right button. There's a degree mark right there. So if you really want to use degrees, go for it that way. But leave your calculator in radians all the time. Well, now if I go to graph something, my graphs are r equals. And we write a polar equation r as a function of theta, or implicitly as some function of r and theta together. Just like we did implicit derivatives back in chapter 3, I can think of polar equations implicitly. We'll look at a couple of those, but for the most part, I'm going to spend my time with graphs that look like this. So let me start with what I think are some easy ones. If I gave you the graph y equals a number, and I asked you to graph that, y equals 2, what would you draw? And x is allowed to be anything I want, right? It's not in the equation, it can be free. R equals 2, theta is not in the equation. It means theta can be free. It means I can be at any angle I want, but I'm at a radius of 2. That's a circle. As a matter of fact, r equals any number is a circle of the absolute value of that number. So if I tell you r equals -2, then you've just backed up 2 units. You're still going at any angle. You're going to get a circle of radius 2. You will almost never see anybody write r equals -2. They'll just make it 2. This one tight. My calculator can't graph this. Because when I go to type an equation on my calculator, it wants it to be r equals. This is the same idea as trying to graph an equation that looks like x equals. If I gave you x equals a number, y equals a number is a horizontal line, x equals a number is vertical. But in my polar graphing, I only have one kind of line. Circles, and then I have lines where they go through the origin at a particular angle. What angle is 5 pi over 6? Way over here in the second quadrant. So this is a line through the origin at 150 degrees. Hey, wait a minute. That's that angle, right? 5 pi over 6. If it's a line through the origin, it's y equals mx. And since it goes through the origin, b is 0. What's the slope of that line? I know the answer to that from doing my unit conversions. Dom, you were the one to tell it to me. Right, I could put a point on here. Negative root 3 over 2 will be over here. And how did you know those numbers? Cosine and sine, right? But then the slope of that line connects this point with the point 0, 0. Yes? So it's sine over cosine. 1/2 minus 0, negative root 3 over 2 over. Wait, sine over cosine is? right up here in the box, tangent is y over x. I have the theta, tangent of theta in this case, is negative 1 over root 3. Oh, you sneaky booger. There are lots and lots and lots and lots and lots of different polar curves. And some of them we use a lot. You can do it with any number. I've just picked 2 for the hell of it. So go ahead and graph r equals 2 cosine theta. Please notice that this button, xt theta n, will give me a theta automatically, just like it gave me an x or a t. If I graph that on the standard window, and I'm going to hit zoom 6 to make sure I'm on the right window, the picture looks like this. That's not a great picture. Let's zoom in a little. Zoom option 2. Zoom in around the origin. So I hit enter again. I think I'm in the same boat I was in last week. This isn't a squared up picture. So I'm going to go back to the zoom menu and I'm going to hit option 5 to square everything up. This looks like a circle. Is it a circle? Or do I have my head firmly planted up my backside? Well, if it is a circle, it should have in Cartesian coordinates x minus number squared plus y minus number squared equals radius squared. Where is the center of that circle? Yeah. And if that's the case, and it happens to go through 0, 0, then the radius should also be 1. Which means I know what the equation of this circle should be. How do I get there from here? I'm going to cheat. And I'm going to take this equation and put in x and y. But before I do that, because of the radius equation, r squared is x squared plus y squared, right? It would be easier if I had an r squared. So let's take this equation and multiply by r on both sides. Now, what's on the left of that equation if I switch from polar to Cartesian? Where I have r squared, I get x squared plus y squared. But then over on the right, I see an r cosine theta. What's that? Aha! Ready for the best part? I'm going to move the x to the other side, and I'm going to complete the square. What completes the square there? Leo. So I add 1 on this side. That means I add 1 on that side. And now on the left, I have x minus 1 squared plus y squared equals 1. Hey, look, the center of my circle is at 1, 0, and the radius is the square root of the other side. This is a circle. By the way, if you do this one, on the right side, instead of getting 2x, you'll get 2y. And that means that this circle looks like this, which we can actually check by drawing 2 sine theta and seeing it's the same exact circle oriented along the y-axis. We will see this duality often. Equations that have cosine in them usually align with the x-axis. Equations that have sine in them usually align with the y-axis. Questions? I'm not going to go through the process of switching between Cartesian and polar very often, because I actually think that polar curves are very pretty and interesting left in their polar equations. Here's one. I think I want to do 1 minus sine theta. Hey, wait a minute, it's a sine theta. Should this curve be aligned horizontally or vertically? Yeah. Probably be vertically. Oh, look, it's a cardioid, a heart. This is why I made sure I used the minus, because if you use the plus, it's upside down. Everybody calls it a butt. I've had a lot of people refer to it as a peach curve. It might be the outline of a peach. And if I used cosine, it would be sideways. But what's special about this is it's one of a whole family of curves. And the reason I got a cardioid is because the number in front of the trig function is also a 1. And the number in front is a 1. So it's really 1 minus 1 sine theta. If I change these, 1 minus 2 sine theta, it doesn't come to a point there in the middle. It draws this little extra loop inside. Whenever the number in front of the trig part is bigger than the number in front, we get that little extra loop. This is called a limousin, after the little cedilla that you see at the bottom of the French letter C, limousin. If the number in front is bigger than the number on the trig part, then we don't get enough dip to get that point, and we actually get a little flat spot instead. Again, this is another limousin. There's limousin with loops and limousin without loops. And it's just dependent on the ratio between these two numbers. All right, cosine theta, 2 cosine theta gave me a circle, right? What if I make this 2 theta? What do you think is going to happen? Don't draw it yet. What do you think is going to happen? Yeah?
Where do you want inward?
Because I'm going around twice as fast, right? The 2 theta should make me go faster around the circle. But because I'm going faster around the circle, I actually move in and out because that changes the radius. Whoa, I don't get a circle at all. I get a propeller. Commonly referred to as a rose, a flower, 4 leaves. Wait a minute, put in 2 theta. I got 4 leaves. What if I do 4 theta? Well, then I end up with 8 leaves. Now it's cosine. The first leaf we drew was on the x-axis. If I do sine, what do you think changes? Say again? It's not on the axis. And because of the symmetry, that means none of the leaves are on the axis. Even if we do 2 theta. Nothing's lined up. I skipped something. What happens when I do 3 theta? Why aren't there 6? there really are 6. They're just on top of each other. Hit the trace button, and you can walk around the curve, right? From 0 to pi over 3, from pi over 3 to 2 pi over 3, 2 pi over 3 to 3 pi over 3. I go back around the exact same loop twice. When my number is odd, I get exactly that many loops, but they're each covered twice. When it's even, they don't line up perfectly, so I get twice as many loops. Now, I did sine. If you do cosine, then your first loop is on the x-axis. Questions? Derivatives. Clearly, I can take dr d theta, but dr d theta doesn't tell me very much. If I want a tangent line, I want dy dx, damn it. How do I get dy dx? I switch back. Almost. What I think about is I think about y equals r sine theta and x equals r cosine theta. So you're right, I'm going to write 2 cosine theta sine theta and 2 cosine squared theta. Yes? And now I do the derivatives of those. dy d theta over dx d theta, just like I was in parametric, only I'm treating theta like I treated t. Now, I could leave this in its general form, but I like doing it this way, multiplying by the thetas at the beginning, and then I can ask, well, wait a minute, I know how to do these derivatives. dy d theta, derivative of the first times the second, derivative of cosine is minus sine, plus derivative of the second, derivative of sine is cosine, times the first. Dx d theta is, oh, that's chain rule. 2 times 2 cosine theta, the derivative of cosine is minus sine. So dy dx can now be worked out. Questions? I'm going to be just a little sneaky here. Please notice, I'm going to go back to chapter 7, our trig integrations, and I'm going to pull out those same double angle formulas we used. What are those formulas? You're not allowed to forget them just because we're not doing integrals anymore. Sine of 2 theta is 2 sine theta cosine theta, and cosine of 2 theta is cosine squared theta minus sine squared theta. Please notice what's up here in dy dx has a cosine squared minus a sine squared. They just both have 2 in front of them. So I could rewrite this as minus 2 cosine 2 theta. And on bottom, there, 2 sine theta cosine theta. So I get minus 2 sine 2 theta. What wonderful thing happens? I can't quite hear you. Not quite inverse tangent, it would be, we flipped it, it's not inverse. Inverse is going backwards and getting the angle. Cotangent. And the minus 2's canceled, so I just get cotangent 2 theta. Which, by the way, you don't have to simplify all the way to there, but I just was thinking cosine 2 theta and sine 2 theta. Because the question in the textbook asked me, where are my tangent lines horizontal? How do you know where a tangent line is horizontal? How do I know those are the right angles? I'm asking a more general question. All the way back in Calc 1, what did you look for to find out where your tangent line was horizontal? Yeah? And a fraction is 0 where the top is 0. So I need to know for what angles is cosine equal to 0. And in this case, cosine is 0, pi over 2 and 3 pi over 2. Oh, well, what? That's 2 theta. So it's pi over 4 and 3 pi over 4. And where is it horizontal? Where is it vertical? It's vertical where the slope is undefined. A fraction is undefined where its bottom is 0. Sine of 2 theta is 0 at 0, and pi at 2 pi. Well, that's 2 theta. So it's divided in half. 0 pi over 2 pi. And that makes sense if I go back and I look at the picture for 2 cosine theta. I can go ahead and I can trace it in. Trace at 0, I have a vertical tangent line. At pi over 4, I have a horizontal tangent line. I can find all these places exactly the same way we did, but now I'm doing it parametrically, just like we did on Friday. Only it's not in t anymore, it's in theta. You know what we're doing tomorrow? Part I didn't get to yet. If I can do derivatives, I need to do integrals. I will see you all tomorrow for that.